Time we were talking about the enthalpy changes associated with physical changes. So we talked about heating curves and calorimetry, and how you can't have a temperature change and a phase change at the same time. And so we went through an example where we start with minus 25 degrees C ice, and we want to see how much heat is involved in changing that to 125 degrees C steam. And so looking at all the segments involved with that. So there are temperature change segments and there are phase change segments associated with that. Today we're going to focus in on enthalpies of chemical change, and then we're going to do some examples of calorimeter problems and heat transfer problems. So we're going to start with talking about the thermodynamic standard state. And so we need to define what that is. And so the thermodynamic standard state is the most stable form of a substance at 1 atmosphere pressure and 25 degrees C. And if we're dealing with reactions that involve solutions, having a 1 molar concentration for all of those solutions. And so it's really just important to make sure we're specifying what state we're in and what the temperature and pressure variables are in a chemical reaction. Whenever you see a variable such as delta H, delta S, delta G, and it has the little degree symbol up here in the superscript, that means that you're dealing with standard state conditions, meaning your pressure is 1 atmosphere, your temperature is 25 degrees C, and all the solutions were 1 molar. That just allows us the ability to compare data, in tables and such. So if you look at any of the appendices in the back of your textbook that have the thermodynamic data, and you're going to be using those a little bit more in the coming chapter, you're going to see that all that data is collected under these same conditions. If we change the pressure, we change the temperature, that's going to cause a change in the enthalpy and those other thermodynamic properties. So let's look at enthalpies of chemical change. Enthalpy is an extensive property, meaning that the magnitude of the enthalpy change is going to be directly proportional to the amount of the reactant consumed in that process. So here we have the combustion of methane. So CH4 plus oxygen goes to form CO2 and water. And in this amount, this is saying that if I have 1 mole of methane and it's combusting, it's going to give me 890 kilojoules of heat given off. Now, if we were to combust twice as much of that, so if I reacted 2 moles of methane, 4 moles of oxygen, it's going to release twice as much heat. And so I would get 1780 kilojoules of heat released. Right? And so the key thing is the amount of stuff that's reacting is going to affect the amount of enthalpy change you have. Another thing, the enthalpy change for a reaction is equal in magnitude, but it's opposite in sign to the delta H for the reverse reaction. So take that same combustion and we're going to turn it around. If we could take carbon dioxide and water and undo the combustion to form methane and oxygen, it would still involve 890 kilojoules of heat. However, in this case, the sign would be positive. So whenever you have reverse reactions, you keep the same magnitude, but you change the sign. And finally, the enthalpy change for a reaction is going to depend on the state of the reactants and the products. So here in example 1 and example 3, all of the species are the same, but you'll notice that when we're dealing with water here, it is now a gas on the right side of the equation. If I look at that reaction, notice that my enthalpy change is different. It's now minus 802 kilojoules versus 890 kilojoules. The reason for that, converting water from the liquid state to the gas state is going to take some energy. And so that 88 kilojoule difference is because I have to convert 2 moles of liquid water to 2 moles of gas. So just to make sure, if we're using values from the back of the textbook and the appendices, make sure we're comparing apples to apples. Make sure you have the right states involved. All right, so let's do a couple of simple examples that involve enthalpies of chemical change. So to start with, we can ask the question, how much heat is released when 4.5 grams of methane is burned in a constant pressure system? Now, you're always going to see this clause, constant pressure system, added to problems, because if you read the first 4 sections of the chapter, whenever you're changing pressure, you're changing volume, that can involve work and the generation of heat, and that could change things. So in all these scenarios, we're going to have a constant pressure system, and that just makes our calculations easier. All right, so where we're going to start is the question is asking how much heat. So we're going to be trying to figure out how many kilojoules of heat is going to be given off when I start with 4.5 grams of methane. And really, we treat these like a regular stoichiometry problem. The only difference is we have one additional conversion that we have to do. So as we start here, we remember that grams doesn't tell us much of anything. And so I'm going to need to go from grams of methane to moles of methane in my first conversion. And to use that, I'm going to do the molar mass. So there's 16 grams of methane in 1 mole of methane. And now to get from moles of methane to kilojoules of heat, I'm going to use the information given in the reaction here. If I take 1 mole of methane and I combust it, I can expect minus 890 kilojoules of heat to be given off. All right? So this is going to be my conversion factor here. Grams of methane cancels with grams of methane, moles and moles, and so now I'm left with kilojoules. And so when we look at everything at the end, I'm going to get minus 250 kilojoules of heat released when I combust 4.5 grams of methane. And again, since enthalpy is an extensive property, the more reaction I do, the more heat. Here, I've only got about 1/4 of a mole of methane actually combusting. And so it makes sense that my heat value is about 1/4 of that overall value. I also want to make sure that I'm keeping track of my signs. So I have a negative and I have a negative here. If you're playing fast and loose with the signs in your calculations, you're going to get the same number, but you always want to check at the end to make sure that if it's an exothermic process, that you have a negative number here. And so I'm expecting, combustion to be negative. I should have a negative number and report that. All right, we can do another example here. Let's talk about the value of heat when 5 grams of hydrogen peroxide is going to decompose at a constant pressure. Again, I'm looking for kilojoules of heat over here on the right. I'm going to start with 5 grams of the hydrogen peroxide. All right, first thing is we want to convert from grams of hydrogen peroxide to moles of hydrogen peroxide. And just do this with the molar mass. All right, so I've got 2 atoms of oxygen, so each of those are 16, so that's 32. So that means there's 34 grams of hydrogen peroxide in 1 mole. And in our equation, we're told that when 2 moles of hydrogen peroxide decomposes, we can expect minus 196 kilojoules of heat to be given off. So 2 moles gives us minus 196. So that's our conversion here. We do the math, and we're going to see that we can have an exothermic reaction of minus 14.4 kilojoules of heat given off in this process. All right, now we can take these problems and we can solve them any number of different ways, right? But at the heart, there's still stoichiometry problems that involve a conversion between moles and kilojoules. So let's take a look at this reaction. We have magnesium is combusting with oxygen to form magnesium oxide. This is a very exothermic reaction at minus 1204 kilojoules. So again, the sign here being negative lets us know that we have an exothermic reaction. All right, now we want to calculate the amount of heat transferred or given off when 2.4 grams of magnesium reacts at a constant pressure. So we have an unknown amount of heat that we're trying to solve for. We're going to start with 2.4 grams of magnesium. Right. And so we need to figure out from grams of magnesium to moles of magnesium. In 1 mole, there's going to be 24.3 grams. All right, now from our equation, 2 moles of Mg is going to give us minus 1204 kilojoules of heat. So grams magnesium cancel, moles, and here I am at kilojoules. And so this is going to give us minus 59 kilojoules of heat transferred in this process. All right, well, let's switch it up a little bit and say how many grams of magnesium oxide are going to be produced during an enthalpy change of minus 96 kilojoules. All right, so how many grams of MgO? That's what I'm trying to solve for over here. And then minus 96 kilojoules. All right, so if I start with kilojoules, I want to have kilojoules on the bottom. And so my conversion is minus 1204 kilojoules of heat are going to be given off, right, if I have 2 moles of MgO reacted. All right, now the problem asks for grams, so I'm going to go from moles MgO to grams MgO here. All right. In 1 mole of magnesium, all right, we need to calculate the molar mass of MgO. So we've got 24 from the magnesium, actually 24.3 plus 16, and so this is going to be 40.3 grams. That's just the molar mass. So kilojoules, moles MgO, and here I am at grams MgO. And go through the math here. We're going to get 6.43 grams of MgO must be produced if we have an enthalpy change of minus 96. All right, and finally, how many kilojoules of heat are absorbed when 7.5 grams of MgO is decomposed into Mg and O2 at constant pressure? All right, so again, I'm looking for how many kilojoules as my answer, and I'm going to start with 7.5 grams of MgO. Now, the way this question is worded, it's talking about the reverse of this reaction, right? So if we were able to turn this reaction around and convert MgO back into Mg and O2, right, we would still have 1204 kilojoules of heat involved, but I'm going to change the sign up, right? So it doesn't really change too much how we solve the problem. I still want to do dimensional analysis. All right, there are 40.3 grams of MgO in 1 mole of MgO. And if we were to do this reaction in reverse, 2 moles of MgO, right, is going to require positive 1204 kilojoules of heat. Again, we're talking about the reverse reaction, so we need to change the sign. And so grams, moles, here at kilojoules. And so we're going to end up with 112 kilojoules of heat is going to be required in order to cause this decomposition to happen. All right, so again, these are pretty much stoichiometry problems, but we're going to use one parenthesis that's going to involve a conversion of kilojoules to moles. And again, we're going to use the information given in the problem to do that.